Here we have another method to solve the first order ordinary differential equation. That's a numerical method. This is called the fourth order Runge Kutta method. And actually, the philosophy of this method is very similar to the second order Runge Kutta method, and but a bit more sophisticated, so that the order of the error of this method in each step goes like a fifth power of the time step delta t. And here I'm just going to present the final difference result, the method itself, but we're not going to present here the derivation of this method. But actually, in order to make this derivation, you can actually follow the same strategy we followed in the case of the second order Runge Kutta method. If you remember, basically there we are just considering a reference time point, which is called tj, and basically we were doing considering like two Taylor expansions around this reference point at two symmetric points, two symmetric time points with respect to these intermediate ones, and just playing with these two Taylor expansions, we're able to get rid of the term which goes proportional to delta t squared, and so that the error of the time step went like a delta t to the third power. In this case, the philosophy is pretty much the same, but in this case, we are going to consider not two Taylor expansions, but four Taylor expansions. So that we're considering another two more Taylor expansions around symmetrically in order to get the approximations for the y functions at four different points, time points, located symmetrically with respect to this reference time tj, and playing with that, with all those four equations, we have to manage to deal with them in a proper way, so that we should be able to get rid of the terms that are proportional to delta t squared, delta t to the third power, and delta t to the fourth power, so that the remaining error goes like delta t to the fifth power. So here, basically, this is, I'm just going to present here the final result. We are waiting for the final difference method for this method. And as you can see, it's an explicit method, and the y point at the next point, as considering the y point, the value of the y value at time ti, just depends on these four different functions that are all the four of them are here defined here. For example, this is the k4, that's one of the functions, which is actually this one. Okay, as you can see, so it also depends on k3, which is defined here, which also depends on this k3 depends on the k2 function, which is also it's defined here, which also depends on k1 function, which is defined here. So in order to apply that numerical finite difference method, you have to first calculate the values of these four different functions, and then plug it in this formula in order to get the next, or the value of the y function at the next time step.